So now we will talk about summation of a function of point and the view over points. So consider a point process with phi, and let us consider a function g, which is a function of point location and the points view, right? So so if you look at this, the view from the point, it itself a point process. So if you take a collection of that, suppose the set and include all such configurations. So this function takes a value from RD and a value from N and map it to a real positive number. So the first one is the points location, and the second one is its mark, which itself a point process. So for example, the realization of PP seen from the point is phi minus xi. So there can be a function g, which is a function of xi, and this view phi minus xi. And suppose we need to compute the summation of this over each point, right? So we need to compute this function of each point and then compute the sum. So we are interested in computing this, going to all point xi, computing this value over that point, sum it, and then what is the expected value of that? Let's call it mg. Okay, so can we compute this? So to evaluate such things, a extension of Campbell theorem is given, which is known as Campbell-Mecke little theorem. This theorem states that expectation of summation of some function of xi comma phi. So this is a function of xi and the point process phi. So expected value of the summation of this function is equal to integration over the whole space, the palm expectation of this function multiplied by lambda x dx. Okay, so basically you can see lambda x dx is the total number of points in the small set dx, and this is the value of the function condition that there is a point at x. Okay, so you can notice this blue and this red phi are actually different. This phi is condition that there is a point at x, while this phi is just has points at x size, right? And then you go to each point and compute this function, take the expectation. Right. So I will not go through its complete proof, but I'll give you a small, compact overview of how this results come into picture. So if you look at this expectation, so what is happening is there are many points xi, right? You go to each point xi and compute function of xi comma phi, and then you sum it over, right? So this expectation basically it's over the whole space, right? So you can divide the space into small sets like this, right? And the total expectation will be basically summation over each of these intervals, right? So this would be that if I divide the area into small intervals, ds belongs to RD, and compute this expectation. Okay, so if I look at a small interval now and just focus on that, so if you take this small set dx, right? So to compute the expectation of this in this area, we need to know how many points are there, right? And if dx is very small, there can be either 0 points or 1 point in it, right? The probability that there are more points, more than 1 point in a small interval is 0, right? We assume a simple point process, so there cannot be 2 points at the same location, right? So if dx is very small, they can be treated as the same location, so the probability that there are 2 points is actually exponentially goes down, right? And so if there are only 0 and 1 point, right? So how can you compute the probability of having a 0 point and 1 point? So suppose having a 1 point only has a p probability and 0 has 1 minus p probability. So expected number of points in this area is 0, 1 minus p plus 1 into p, right? And that should be equal to lambda dx, right? This is the expected number of points, and this is also expected number of points I calculated. So from this you can guess the probability that there is a one point is equal to lambda x dx. Okay, so what I do is uh, condition this expectation of so I want to compute this in this interval only, right? And then I will sum it over the each of these small intervals. So if I focus on this set, the expectation of this would can be given as probability that there is 0 point in this set, right? This is the number of points in the set is 0, multiplied by, if there are no point, then the expectation is value of this random variable itself is 0, plus if there is 1 point, okay, multiplied by the expectation of this function, okay, condition that there is a one point at x, right? So you want to compute this expectation. So what I did is I first condition on number of points, right? So I applied a total probability law, total condition probability law. So if there are no points, then the value is 0, plus if there is 1 point, then this summation would be just a 1 point, so fxy, and then you because I conditioning on there is a 1 point here, this is condition that this is condition that phi dx is 1, okay, and then there would be that phi dx is 2, but the probability of that would be very small, right? So we can ignore that. So as ds goes to 0, this probability becomes more and more negligible, so that's why we have excluded it. Now if we look at this, the first part is just 0, so, and the second point I have to take probability phi dx is 1 is lambda x dx, okay, and then multiplied by this expectation. Notice that this expectation of fxy condition that there is a point at x, so this is nothing but the expectation, okay. So this is only for a small set ds. If I want to compute the overall this summation, what I have to do is I have to sum it over all the sets dx in Rd, okay, and as dx goes to 0, right, this will limit to integration over Rd of expectation fx comma phi lambda x dx. So this is how we are getting this result, right? And you can basically also understand this in the way that these are if I divide into small interval, these are total number of points in the set, and this is the expected value of the function, assuming that there is a point at x. So that is the basic version of the Campbell-Mecke little theorem. But there are multiple versions also available which can be applied for different applications. And they are basically the same thing, it's just in a different way. So first one is a reduced version. So reduced means that you somehow want to have a function says that when the phi second input phi comes, you don't count the point on which don't count the point xi in the view. Okay, so let's take f xi phi is a function which is basically a function of xi and phi minus xi, right? So this function, when I compute, I give it xi in phi, it computes over the point location xi, and in the view it did not consider xi, so it removes xi from that, right? And just compute it over the rest of the points, right? So this is a can be written as a functions g, some other function g of xi and phi minus xi, right? So in this you just give whatever you give, it computes on that. So if the function f is like that, you can write f in this form. Right. So g takes the reduced version of phi, and if I put this here, what I get is instead of f, I get g of xi comma phi minus xi. So this is a function which takes xi and the view after excluding xi from it. Right. And then also I have put g here. So this will be integration of rd, expectation of gx phi minus x, right? Lambda x dx, right? So if you look at this fx comma phi, if you put it here, then we just get that this is equal to g of x in phi minus x. So you remove x from phi, lambda x dx, right? Now if you look at this, this is nothing but just a reduced palm expectation of gx phi, right? So this is has the same meaning that you compute gx phi, but you condition on a point x, but you exclude the point from phi, right? So either I write in this way or this way, this is same. So if you use a reduced version in the left hand side, you also get a reduced version, reduced palm in the right hand side. Okay, so now let us see how this we change this for the stationary point process. So if stationary point process means you shift the point process and this distribution does not change, right? So if you look at this original expression, there may be some problem that you have to compute the palm expectation. So this is an integration over all point, and then you have to compute the palm expectation condition on x, right, for every x, right? And then only you can evaluate this expectation. So for some people it may be tiresome for some problems that you have to compute this palm expectation for every possible x. Right. For stationary, this problem can be reduced a little bit. So if phi is a stationary point process, then assume there is another point process phi dash, which is of course dependent to it, such that when you shift phi dash to x, you get phi. Right. So in other words, basically phi dash is phi minus x. So this is, you take phi, you shift it by minus x, you get phi dash, right? So conditioning on a point at x for phi is same as conditioning on a point at origin for phi dash, right? So if there is a point at x in phi, when you do minus x, you get x will be moved to origin. So conditioning on a point at x in phi is same as conditioning on a point at origin, right? One thing I'll like to clarify is, see, this minus is different than this minus, right? So this is a set minus. It means you take phi and if there is a point x in phi, you remove that. Okay, so there is no shifting here. It's just that all points are same, only the point at x is removed. In this case, you are not removing any point. You are taking the point process and you are subtracting vector x from each point, so that the overall point is shifted. Okay, this is just for clarification. So okay, so now if I look at this expression, this is the palm with respect to phi. Can I write in terms of phi dash, right? So, right, you can think that phi is equal to phi dash x. So I can put phi dash x here, right? But now my main process is not phi dash. So the probability is with respect to the expectation is with respect to the distribution of phi dash, right? So when I say in this case I put x because I'm computing the expectation with the phi. So there's a point at x in phi. Here I'm computing the expectation with respect to phi dash. So what I do is I have to write from the perspective of phi dash. Right? So if there's a point at x in phi, there would be a point at origin in the phi dash. Right? So this is same as saying that this is the palm expectation of fx comma phi dash x with respect to the point process phi dash, condition that there is a point at origin in phi dash. Okay. So this is what I get. Now we will notice that phi dash and phi. So forget about the rest. Just look at this particular part, right? Right. This is deterministic integration. right? And expectation with respect to phi dash is only here. Now you can notice that phi dash and phi has the same distribution because of stationarity, right? So phi is a stationary process. So if we shift it by x, it still has the same distribution. So whether you compute the expectation with respect to phi dash or phi, you would get the same result, right? So I can just replace phi dash by phi here, and the result will not change. So what I get is, and of course for stationary lambda x would be lambda, so I would get lambda integration on RD of palm expectation conditional point at origin of f comma fx phi x dx. Okay, is right. So the benefit here, we know this by Campbell-Mecke theorem, and the benefit here is that in this case you don't have to compute expectation for every x. If you know just the probability palm expectation with respect to a point at origin, that's all you need, and you just put it there and then integrate this function. Okay. Again, notice that here the phi has point xi, right? This red phi has point xi, while the phi is conditioned that there is a point at the origin. So phi x would have a point at x. Okay, so phi x is conditioned on a point at x, and the red phi has point at x. It's an unconditional point process, but here this is a conditional point process. So somehow Campbell-Mecke or theorem of Campbell-Mecke little theorem, they connect the unconditional point process to the conditional point process, right? So if I have a summation over the unconditional point process, how can I write this in terms of a conditional point process? Okay. And to further solve it, you would require a knowledge of palm expectation. If you have it, then things become easier, right? We would learn one more version of that, right? Which sometimes known as Campbell-Mecke's theorem, and they are basically all same thing, just different forms. And here you take assume the function. There is the second argument you want to take is not the just the phi, but it is a view from the point. Right? It's a shifted version of phi, right? So. So let's consider a function g x comma phi minus x, right? So this is a function which takes the point x and the view of phi from x. So you shift the point process to this point x. You look at that. That is the second argument of the function, right? So because this is also a function of x comma phi, I can just put this here, right? And in the original Campbell-Mecke theorem, and this should still be satisfied. So if you put it there, the left hand side you get summation over all point g xi comma phi minus xi, and in the right hand side you get lambda expectation 0 g x comma phi, right? Because phi is instead of phi you have phi minus xi. So if you shift it, so this will be phi minus x, and then you shift it again by x. So if you take phi, shift it by to minus x, and then you again shift it to x, you just get phi. Right. So this just means that if you have this kind of function, you go to each point, take the point location and the view, compute the function value, take the summation, compute expectation. That is just equal to integration of palm expectation of the function at x comma phi, condition that there is a point at origin dx. Right. Here you can notice that this phi minus xi has a point. So phi has a point at xi. So phi minus xi has a point at origin. Right. Here also phi has a point at the origin. Right. So basically the same thing. Here you go to the this thing, you compute the function x, and then you condition that there is a point at the origin. And you compute that. Right. If you compare with this, the view is the perspective is similar, because here also you have this function. You take the point xi, and then you take the point process at xi, shifted at the xi. So the phi minus xi still looks like there is a point at the origin. Right. And just note that, just to be explicitly saying, this palm expectation is the expectation of function with respect to the palm probability. Okay, so P0 d phi is the probability of occurring of this realization d phi condition on the fact that there is a point at the origin, right? And then with respect to those realization, you compute gxi and then integrate it over the all possible realization, conditional realizations. Okay, so up to now we had computed uh, we have taken the actual Campbell-Mecke little theorem, compute the reduced version of it, then we compute for the stationary version, right? And then now and then we use the shifted version. So now what I will do is I'll take the stationary process, shift it, and also use the reduced version, right, together to see how what will be the form. And this is also used a lot. So Campbell-Mecke with reduced function, what I do is in this case I've already have this x comma phi, and what I do is instead of phi I want to have a reduced version, which means the view does not include the point xi. So consider a function fxi comma phi gxi phi minus xi. So now if I put it there in the left hand side, I get this. So I'm going to each point and computing this xi and phi, and the second argument is phi, but the xi is removed. Right. So in the right hand side, when you look at this, again you get the same thing. You would have phi x, but the point x would be removed. Right. The point at the origin should not be included in phi. Right. So to formally say it, I'll just put g here, right? Instead of f, I have this g xi f I minus xi. If I put it there, I get e expectation, palm expectation g x comma phi x minus x. Right? Set minus x. Right? I just put the definition of x. Right? So removing x from phi x is same as removing 0 from phi and then shifting it. Right, the same thing. So either you take the phi and shift it to x and then remove the point at x, or you remove the point origin from phi and then you shift it by x. Okay, so what I basically get is this is a conditional probability that phi has a point at origin, right? And I want to remove that point and then shift. So this is nothing but just a palm expectation, e reduced palm expectation, e 0 exclamatory mark g of gx comma phi. Okay. Now let us see how does it look like for Poisson-Point process. So in Poisson-Point process, you know that probability of phi minus 0 belongs to p, condition that there is a point at origin, is same as the unconditional probability that phi has property p. Right. So if you condition on a point at the origin and you remove that point, and then you ask whether this conditional phi has property p, the probability would be same as just the unconditional probability whether phi has p or not, right? So if the probability is same, expectation will also be same. So this expectation would be same as e of g of x comma phi x. Okay, because what I do is I'll remove the conditioning and also remove the point. So I get this. Right. So now notice that now there is no conditioning here, right? So lambda e of g x comma phi x dx, right? And because there is no conditioning here, whether you take phi or you take phi x, both mean same thing, right? Because you are not conditioning on any point, right? Just a expectation respect to phi x, and phi has the same distribution because they are stationary point process. So I can also write it just in terms of e of g x comma phi. Right. You could have gotten the same result if you have used the if you have used the shortcut view version also 5 minus Excel. Yeah, understand. Here also if you use it for PPP, basically this will be just removed and you get E of Gx comma 5. Now look at some application of Campbell-Mecke theorem. The first example we will take is the cellular case when you have instantaneous association with or without fading. This is the case this is a scenario which we started in the chapter 7, but the downlink performance case, but we then left because saying that we would require Campbell-Mecke theorem. So let's go back to this application and let's see how we can use Campbell-Mecke theorem for this problem. So this method basically works only when SINR threshold is greater than 1. And in particular, when the instantaneous power is exactly equal or the linear multiple to the received power level. Okay, so remember in the general cellular definition, we have a received power level, and this works when you make a decision, the value you are making a decision on, which is the received power level, is actually same as the instantaneous power. Right, which is basically a definition of instantaneous association. In instantaneous power association, you make the association decision based on the instantaneous power itself. So, so there are multiple steps to understand this method. So let's see. Let's start with why the threshold getting 1 is required. So consider a system with 2 base station. And if we suppose there are 2 base stations are there, and then there's some noise, so we have to select between these 2 base stations, right? Which one we want to select, and we want to do the instantaneous base association. So denote the receive power from the 2 base station at the mobile user by A1 and A2. So if you select the base station 1 as serving base station, the SINR would be A1 upon A2 plus sigma n square, which we call SINR 1. And if you select the second base station, then the SINR would be A2 upon A1 plus sigma square, which is SINR 2. Right. So if you select first base station, of course, A1 would be in the serving power and A2 will be in the interference. And if you select the second base station, A2 would be serving power and A1 would be the interference. Right. So if A1 divided by A2 plus sigma n square, the SINR is more than 1. Right. This means A1 is more than A2 plus sigma n square. Right. So this also means that A1 should be more than A2. Right. If A1 is more than A2 plus something, then A1 is of course more than A2. Right. So if A1 is more than A2, this means A2 upon A1 is less than 1. Right. Which further implies that A2 upon A1 plus sigma n square is less than 1. Right. So SINR 2 is less than 1. So if SINR 1 is more than 1, then SINR 2 is less than 1. Right. And similarly, you can also show if SINR 2 is more than 1, then SINR 1 is less than 1. Right. So only one of the 2 SINR can be larger than 1. Right. If one is more than 1, then the other one will be less than 1. Right. And this is true for not just one, for any threshold more than 1. So out of 2 base station, only one can give you SINR more than threshold, if threshold is more than 1. Okay. So if we want to have the target SINR for all TS to be more than 1, the coverage condition can be met only by at most 1 base station, right? It may happen that none of the base station give you more than 1 coverage, right? If all are very far away. But if they do, only one can give you more than 1 0 dB coverage. Okay, so if you denote the index of serving base station with highest SINR by 0, and its SINR by SINR 0, then we can say that SINR 0 is equal to max of SINR 1 comma SINR 2, right? Right, which means I'm selecting the base station which is giving me the maximum SINR, In that case, I can, if I want to compare these two following scenarios, when the event that assigner 0 is more than tau, and the summation of indicator of assigner 1 is more than tau plus assigner 2 is more than tau, right? So if you look at this one, assigner 0 is more than tau if uh, either assigner 1 is more than tau or assigner 2 is more than tau. Okay. Uh, and it will be 0 if none of them is more than 2. And in this case, you can, in this right hand event, you can look at, I'm adding two assigner indicators, and since only one assigner can be more than tau, right? So if assigner 1 is more than tau, then the first indicator will be 1 and second indicator would be 0. Summation would be 1. If assigner 2 is more than tau, then also the second indicator is 1, but the first indicator is 0, the summation is 1. Right? And if both SINR is less than tau, then the indicator would be 0. So this is also takes, they also takes value 0 and 1. 0 when none of them is more than tau, and 1 when either one of them is more than 1. Right? So you can see, compare that this left hand event and the right hand event are actually same. Okay, and this is because only one of the SINR can be greater than tau. Right? So for every possible values or for every realization of SINRs, these two events are same, right? And this result we can extend for more than two base stations also. If there are n variable a1, a2, an, and if we define ai upon sigma aj plus sigma square as si, so for every I, right, you denote ai upon sigma aj plus sigma square, then you can show that only one SI can be more than tau for all tau greater than 1. Okay, and it is possible that none of them is more than tau, but if there is one, then there can only be maximum one I for which this is more than 1. Okay. And certainly you can also show that AI for which it is possible should be the maximum of all ages, right? Of course, more intuitive that if this is ever more than 1, then you should basically choose the maximum AIs on the top so that this will not appear in the denominator. Okay, so now this AI you can think of as receive powers, and then SI as the assigner if the ith base station is selected. Then you can show that if the assigner I is more than 1, then it can only be for 1 I. Okay, so let assigner I denote the assigner of a typical user at the origin from its associated base station, given that it is associated with the ith base station at location xi. Then assigner I is given as receive power divided by interference per sigma square, and this interference does not include the power from xi, right? But the rest of psi. If tau is more than 1, then you can show that the indicator that the maximum SINR is more than tau is same as if I go to each base station and check whether their SINR is more than tau and sum them over, right? Since only one of the SINR can be more than tau, this will be 1 if any one of them is more than tau, right? And that is, and of course, the maximum should satisfy this condition. So this indicator and this indicator are basically same. Because the event is same, therefore the probability should also be same. So if I take probability on both sides, expectation on both sides, what I get is expectation of indicator, which is probability that SNR more than tau is equal to expectation of summation of xi SNRi more than tau, right? And this is nothing but the coverage probability, right? In the instantaneous association case, you are associating with the maximum SNR base station. So if that base station is more than tau, then of course you get coverage is more than tau. So coverage probability here is can be written as summation of expectation of summation of indicator over all points of SINR more than tau. Right. That is the first step in understanding that you can actually write down this coverage probability in terms of expectation of summation of functions of x. Right. This is not in that form. Right. If you cannot convert this, you cannot apply Campbell Mecke. But because tau is more than 1, and you can show that this is actually can be written as summation of indicator over all xi's. Right. So once I get this, I should be able to apply Campbell theorem because the SINR is a function of xi and phi minus xi. Right. Xi because of solving power and phi minus xi because the interference is coming from all phi except xi. So yeah, SINR is nothing but a function of xi and phi xi. So it's a summation of SINR xi comma phi xi over this thing. So I can apply Campbell theorem. So Campbell theorem states that this, and this is a PPP case. So the palm expectation, reduced palm expectation, it will be just converted to the regular unconditional probability. So this will be given as lambda integration 0 to infinity of the probability that SINR x comma phi 2 is more than tau dx, right? And this phi 2 is same distribution as phi. Okay, and this is unconditional phi 2 because of the PPP. So first there was a conditioning on phi 2 that there is a point at origin and you removed that point from phi 2, but because of sim lag you can also remove that. Right, so I have applied Campbell Mecke for PPP in this case, and then what I get here is right. So in this first case, I am not including any fading, right? So receive power is just x distance from my alpha. Similarly, interference is also summation of xi minus alpha plus sigma square, and then there is a PT normalization by PT. So this is the association without, this is a cell network without fading, right? And Right. So remember, we tried to solve this in the earlier case, and then we were stuck with, we were not able to proceed because there was no fading. So here, what I get is this term. Now again, I can put this here, and what I get is integration of probability that x minus alpha tau inverse is minus sigma square less than this. Right. Now the problem is there is again this probability term coming where you need a CDF of I, which we don't know, right? So, but here the interference is without any exclusion region, right? In the previous case, they were in the cellular network, they were in I, which depends on the exclusion region. But here, remember that this I is coming from phi 2, which is just independent. There is nothing, no conditioning. There's summation over all xi's. So there is not like it is the closest base station or like that. So this I is the unconditional interference without any exclusion. But the problem is we are still stuck because we require a CDF instead of Laplace. If we have fading, it may be possible to convert the CDF to Laplace transform. Right. So we now show that we can turn this base station network to another one with fading. Right. So what I do is I have taken the cell network without fading case. I can convert it to a cell network with fading but instantaneous power association, and then I will compute the distribution of coverage probability of that. Right. So in doing that, I will do two things. One, I will compute the instantaneous the coverage probability of the cell network with instantaneous fading, and then I will also show that this would be can also be used to compute the performance of a network without any fading. So I will now compute the coverage probability of a network without any fading and the closest distance based association. And we have seen in the past that it was not normally difficult to compute it, and even when we applied Campbell-Mecke theorem, we were stuck because we needed the CDF of interference and we only had the Laplace of interference. So to make this tractable, actually what we learned in the past that you can create equivalent cell networks which has a similar coverage probability. Okay, so here you can also convert fading to an equivalent network with fading. Okay, and so based on what we have learned in the past, you can convince yourself uh, that the following network is equivalent to the base station to the cellular network without fading. So this network has a base station as PPP, and its density is given by lambda divided by e to power s 2 by alpha. Okay, and h is nothing but a exponential random variable, um, which denotes the fading here. So base stations are denoted by xi comma hi, which is a marked PPP with independent mark hi with exponential distribution. Okay, the power level is given by the instantaneous power, so which is fading into path loss, and then you select the base station which give you the maximum instantaneous receive power based association. So your instantaneous receive power is same as your level. It already has fading, and sin r is given by the ratio of certain instantaneous power divided by the total interfering instantaneous power plus noise. Okay, and then you can show that this is equivalent to a base cell network with uh, with uh, with base station density lambda and base station point at xi with no fading, and because there is no fading, the power level is x minus alpha, and you select the one which gives you the maximum power level, and instantaneous in that case is also equal to the power level because there is no fading. Okay, and then you can just show that because of this moment, both equivalent networks will give you the same assigned coverage. So now I will proceed to compute the coverage probability for this network, and then you can show that and you can then using this equivalency, that will also be the coverage probability of a network without failing. Okay, so let's see how we can compute for this case. So basically what we want to do here is the compute fading and instantaneous power based association. Okay, so instantaneous power based association means uh, you want to select the base station which give you the highest instantaneous power. Instantaneous power include the path loss and the fading. Okay, and previously when we want to compute did the association based on the average power, then we do not include this fading. So that is the main difference between this and the previous average received power based association. So assigner in this case is given by h0 x0 minus alpha divided by summation over hi xi minus alpha plus sigma square. Now using the previous, you can show that if I ask, so this is the base station 0. If I select that, the assigner from that is known as assigner 0. So indicator that assigner 0 is more than tau is basically means that we go to serving base station, which gives you the highest instantaneous power, and ask, is your assigner is more than tau or not? Or we can go to each base station and ask him that if you become the in-serving base station, the assigner provided by you, whether that is more than tau or not. And we have shown in the past that for a single realization, for each realization, you can show that this indicator is equal to summation of this indicator, because there can be only one base station which can provide, for which this indicator can be true. Okay, and right, and the proof on a similar for ways you write the assigner, and then you can treat as AIs, and then you can show that this ratio can only be more than one for only one pi. Okay, so above result is true for only tau greater than 1. For tau less than 1, it may be possible that there can be more assigners above that, and then the result become invalid. So now since the indicator is same for each realization, if I apply expectation on both sides, that will also be equal. So expectation of this indicator is equal to expectation of this summation. And expectation of this indicator is nothing but the probability that a scenario is more than tau, which is nothing but the coverage probability. So coverage probability is equal to summation over this SI. And this indicator is nothing but is a function of xi and phi, or in particular phi minus xi. Uh, and we have to compute this expectation now. Okay, so if there was just a summation of sigma fxi, we can apply Campbell theorem. But here we have a function which is a function of point location and the point process. So we can't apply Campbell theorem. For this, we need to apply Campbell-Mecke theorem. So indicator, let's see how do we apply that. Indicator as an negative is more than tau. I put back the value of SI, which is this. And now if you look at this, this is a function of xi. This is an interference which is a function of phi minus xi, because in this indicator you take the complete phi but you remove xi, and then plus noise is more than tau. Okay, now there is one random variable hi which is independent of the rest, so I can compute I can first compute average with respect to hi. Okay, so what I can do here is I can take this expectation with respect to hi, which comes inside. Okay, because they are independent of points, and they're also independent of each other. So this indicator becomes probability that this value is more than tau. Okay, and if you take back this just become probability that hi is more than tau into I plus sigma square into xi alpha. And using the exponential random variable, uh, this probability is given as e to power minus, right? Probability h is more than t is equal to e to power minus t. So this is just equal to e to power minus tau interference plus noise into xi to power alpha. So now if we have this, which is expectation with respect to phi summation over this thing, and if we look at this is a function of xi and function of phi minus xi. Okay, and phi minus xi is in the form of interference. So if you see this as a function of gxi phi minus xi, this is nothing but expectation of summation of gxi comma phi minus xi. Now you can apply Campbell theorem, which state that this will be equal to integration of lambda gx phi dx. Okay, so I have used the Campbell-Mecke for the PPP here. So condition that there is a point at xi and the point is not included, that will be removed to just get expectation lambda integration of gx phi dx. So what is gx comma phi? That will be equal to g. I'll just put instead of xi, I'll put x, and instead of this, I will put phi. So I get expectation of exponential minus x to power alpha tau I phi plus sigma square dx. Note that this is I phi, which is the interference from all base station, right? There is no conditioning now. So this phi is a complete point process. So as phi I phi is the interference from all points, right? We are not excluding any point now from the point process. So this is easier to compute because there is no conditioning on I. There's no exclusion region here. So this will be equal to lambda integration of this. And now this is expectation of phi. So noise term is independent of phi, that will come out outside, and then rest will be e to power phi expectation is to phi of exponential minus to power alpha tau I dx. Now this is nothing but the Laplace transform of interference computed at x alpha tau. And then if you convert to polar coordinates, this is what you get. Okay, so now only thing is remaining is compute the Laplace transform of interference. Here is no distribution of I, just we need require the Laplace transform of interference. Okay, and the Laplace transform interference is given by e to the minus si, which is given by summation of x s
Hj to power minus alpha, and there is no excellence region, so it includes all points. Okay, so I can now apply Campbell, sorry, the PGFL of PVP to, or the Laplace function of PVP to get this one. Okay, so there is expectation with respect to the mark H in this. Okay, and we can solve this in the same way we have done in the past. You can first transform, use the substitution sh divided by alpha is equal to 1 upon t by alpha. Once you do that, this h to 2 by alpha term will come outside, and rest will be independent of h. And because this expectation is only with respect to h, this term will come outside the expectation. So what I get is e to power s2 by alpha. Then there is an integration, the t dt, and then there is the remaining term is here. Okay, and this integration we have already computed in the past. That is given by 1 by 2 gamma 1 minus 2 by alpha. So once I put this back, I get this term, and the expectation of S2 by alpha for Rayleigh fading, it is gamma 1 plus 2 by alpha. And if you multiply the two, what you get is 2 pi alpha cosec 2 pi alpha. So this is the Laplace interference which I get. If I put back in the expression, what this is what I get. Okay. So there's still integration with this, but it's a simple integration. And if in interference limited case where there is no noise, I will put sigma square equal to 0. So I will get only this term. And if I, this can be integrated very easily to get 1 upon tau 2 by alpha 2 by alpha cosec 2 by alpha. Okay, so this is a closed form expression you can get for the no interference case. Also, when parallel exponent is alpha equal to 4 and it's no noise, then you can further solve it to get 2 pi by root tau. Okay, and if you compare it with the coverage probability derived for the average power association, you get this term. Okay, and you can show that this coverage probability is more than the coverage probability in the average power based case. Okay, and basically if you want to compare, then you want to show that instantaneous power based association is better than average power based association. So you can construct a coupling argument to show that. In instantaneous power based association, we select a base station depending on the criteria that H0 H0 minus alpha provide maximum SINR in comparison to all other base stations. While in the case of average power association, you select the base station depending on a distance only. Okay, sometimes it may provide the highest SINR, sometimes it may not be the base station providing the highest SINR. It may happen the base station which are far away, their fading is good and they are providing you more coverage. Okay, so instantaneous power based association does provide the better SINR for all realization. The following two example can show you this fact for the two cases. If you take two base station and suppose A0 is the fading and P0 is the average power for the first base station. Similarly, A1 is the fading and the P1 is the average power for the second base station. If you select base station 0, the SINR would be A0 P0 upon A1 P1 plus sigma square. And if you select base station 1, the SINR will be A1 P1 upon A0 P0 plus sigma square. So in the instantaneous power base association, if A0 P0 is more than A1 P1, you select base station 0. Otherwise, you select base station 1. So power base association, it will be actually the maximum of the two divided by the minimum of the two plus sigma square. Okay, and you want to say that this coverage would be there when this SINR is more than 1. Okay, while in the case of average power, you just select based on P0 P1. So SINR is actually given by max of P0 comma P1 divided by A1 minimum of P0 comma P1 plus noise, right? So I want to compare these two. This is the SINR. So let's ignore noise for some case. For the instantaneous, you want to compute maximum of the two terms divided by the minimum of two terms, and then for average power, you want to compute the maximum of P0, P1 and uh, minimum of P0, P1, H2. Right? It is clear that although the left hand side always guarantee that you select the maximum of the two, in the left hand side there may be cases when you do not select the best of the two assigned power. So, but you can always say that whenever A0 P0 is more than A1 P1. So basically, you can show that this left hand side is always greater than right hand side for each realization. Okay, so on the average, the instantaneous association will give you more coverage than the average power-based association. Okay, the instantaneous power-based association is actually better, but the problem is if because the feeding is changing at very fast, it may happen that you have to switch the base station, and when you switch the serving base station, it requires some handoff, and some overhead, which maybe can create a lot of which can actually take a lot of resources if this is happening very fast. So you have to create a trade-off that if the network is very fast, you can have to do with the average power based station, even if it is not giving you very good coverage. Okay, but if the fading is changing slowly, then we can actually go for instant power based association, and that what happens in the shadowing case. Shadowing is also is like a fading, but it's a small as a slowly changing fading. So because it's changed slowly, we generally include shadowing in the association decision. We have computed the coverage probability for instantaneous power-based association with feeding and using Campbell theorem, and this is what we get. So we have a point process X, which is a marked point process containing locations and HI, density is lambda, and we show the coverage probability can be written as expectation of indicator of SNRI more than tau, and which is given by this formula. And here I is a unconditional Poisson-bound process, right? Interfering base stations are everywhere. We can also we have also equivalently compute the association this coverage probability by first converting the PPP using to a network to a cell network without fading. So you can show that you can have an equivalent Poisson-bound process with yi such that yi minus alpha is equal to hi xi minus alpha, and then yi's will form a Poisson-bound process with this density. In that case, you would require, because here the association is based on distance. So you would compute the serving base station distance, which is given by this, and then condition on that you will compute the uh, probability, the interference CDF. So the coverage probability would be given as 2 pi lambda e integration of probability I is more less than r minus alpha tau minus 1 minus n e to 9 lambda pi r square r dr. Right? This is given because your first condition on the survey based on distance, compute that coverage probability is more than tau, and then you decondition it. Now to compute the CDF, I will apply Gil-Pallas lemma. I know the Laplace transform. So using Gil-Pallas lemma, the coverage probability can be written in this form. Okay, here I is the conditional Poisson-bound process, the interfering base station outside the exclusion region, which is the ball of 0, r. So this coverage probability and this coverage probability, if you compute them numerically, they are equal, right? Because they are both denote both coverage probability for the same network. But inherently, these two expressions are very different, right? This one is looks like closed form. If you assume noise is 0, you can even compute exact expression, closed form expression. But this is a very complicated expression which requires integration over complex numbers and imaginary point. It's actually really more difficult than to compute than this, right? Even for when noise is 0. So somehow you get two different types of expression using two different methods. They are inherently same, but their field is very different from each other. So now we will take another example, which is cellular network with average power association. And we will look at, so this we have already done, but we will look a new approach using Campbell-Mecke theorem, and we'll show that the answer is same. So a new approach would be using first trying to convert, rewrite the probability coverage expression in terms of summations. So if base station at xi is a serving base station, SNR from this base station at the typical user is given by this expression. Let's call it SNRI. And the serving base station, which is selected as the one which is closest, right, or which is maximizing the average power, we denote it by 0. The assigner from that is known as assigner 0. Okay. Now we are interested in computing the coverage probability from this serving base station. Probability that assigner 0 is more than tau. Okay. To apply Campbell-Mecke theorem, you need the form in the summation over points, as we achieved in the instantaneous cessation case. But if you look at here, if you try to write this, so indicator SNR 0 is more than tau is not equal to summation over SNR more than tau. These two are not equivalent in this case, right? Why? Because SNR 0 is the one which is closer, the closest base station, right? While this one is the base tau is more than 1. Even in that case, assigner I would be more than tau for only one case, and that will be for the one which has the maximum assigner I. Okay. So it may happen that that base station is not the closest one. So this will be 0, but this will become 1. So you can observe that in those cases when the closest base station is not selected, sorry, the closest base station is not the one giving the highest assigner, these two will not be equal, right? And this will be 1, this is 0. These are certainly more terms. Okay, to be able to write them down, I would require one more indicator here, which is will come from the association. So I want that the cases when I only select the base station, which is I only check the whether SN is more than tau for only that base station which is selected one, right? So I define a new indicator SI, so, which is indicated that for XI, for the ith base station is the closest base station among all the points, right? So if xi is the closest base station, si is 1, otherwise it is 0. And now you can write their equivalent. Indicator that SNR 0 is more than tau is equal to summation over SNR more than tau, SI x5 minus xi, right? This SI is a function of location and the rest point process removing xi, as you can see from this notation. So now if you compare them, whenever S0 is 1 and rest SIs are 0. So if you put that here, you will get that SNR 0 is more than tau in the left hand side, and that is also the right hand side. Okay, so now it means I can equally write this in terms of this. So probability of this is also expectation of this, and therefore the coverage probability is given at the expectation of summation of this term, right? Now this again is some function of xi and phi xi, so I can apply Campbell-Mecke theorem to get indicator expectation, sorry, integration of expectation of SNR more than tau into Sx phi comma dx, right? So here again the phi minus xi becomes phi, and the expectation, sorry, the conditioning with respect to that there is a point at the origin that is last. Okay, now you can break this, you can compute the probability of S, and then you condition on S here. Okay, I applied a to chain law that the expectation of A into B is expectation of A into indicator of B is condition probability of B, and expectation of A condition B. Okay, so now you have to just solve this. This you can solve in the following format, and this you get like here, right? So what is the probability that Sx phi right? Which means this is 1, and the base station at x is 1, which means x is the closest base station. It means no other points of phi is inside this ball of x, and that is given by 2 minus lambda by x square. Okay, and here you get this where I is condition on s, so there is no point of phi uh, inside the ball of x, 0 comma x. Okay, so if you apply this, what you get is this expression e to the power minus s alpha tau n. This is noise expression, Laplace transform of I at x alpha tau and e to the power minus lambda by x square dx, which is coming from the probability of s. There here I is conditioned on s, so I is interference from all the base stations which are outside the ball of x. Okay, so this is the expression you got, which is same as what we have used in the SL network case, in the average power case, but this is more rigorous proof than the previous case. Now we will consider one more example. Uh, we want to compute if there is a function on the links, right? Not on the points, not on the but on the links, and we want to compute a summation over those function. How we can compute? So let's see. Consider links xi to xj. So if there xi and xj are two distinct points of a point process, then you can construct these links, right? So if there are n distinct point, then each n point can be linked with rest n minus 1 point. So total there will be n into n minus 1 by 2 points. Okay, sorry, links. So let us assume we only consider a specific set A and B, and the first point of a link should be in A, and the second end point of the link should be in B. That is just for specific case. You can of course take A and B to complete RD. Let a function f x I comma j defined over this link. So this is a function of link, right? It takes two input, the first endpoint and the second endpoint, and give you something, right? So what can be example of function? It can be just the link distance, right? So it will be norm of xi minus xj, okay, or some function of that. So suppose I want to compute the expectation of links, right? So I want to compute the sum of function over all links and take the expectation, mean value of that. So formally I can write it expectation over summation of over xi belongs to phi intersection A. So phi which is inside A, and xj belongs to phi inside B, and xi should not be equal to xj, and the function is f xi comma xj. Okay, so how do we compute this? To compute this, I need to break this into two different summation. One will be summation with respect to xi, and second, the inside summation would be over all xj's such that xj not equal to xi. Right? And these two are equivalent because this is summation over all possible pairs. Here, I've written just in a different way. I've taken the first point first, and then the second point is uh, then second summation is over all points of the second endpoint. Okay. Now, if you look at the whole thing, this is summation over all xj's in phi, excluding xi, and this is some function. So this overall is nothing but a function of xi and phi minus xi. Okay. So xi because xi is there, and then phi minus xi because you are only averaging, summing over all the points which are in phi but not xi. Okay, so this is just some function g xi comma fi, which, and then you have summation expectation. So I can apply Campbell Mecke theorem to get lambda integration expectation, palm expectation condition that there is a point at the origin of gx comma phi dx. Okay, and x comma phi is what? Instead of xi you just put x, and instead of phi you put phi minus xi. Okay, so this is what we get. Okay, now to further solve it, what I can do is I can take xj equal to yj plus x, okay? And in that case, yj plus x belongs to uh, 5x minus sign minus x. It means yj belongs to 5 minus 0. Okay, so again, this condition xj belongs to b means yj belongs to b minus x. Okay, so I am rewriting this expression in terms of new variable yj, which is the relative distance of xj from x. So if you put that, what you get is uh, yeah, instead of xj, yeah, so xj is yj plus x, right? And so here we have yj belongs to 5 minus 0, f of x comma yj plus x indicated that yj plus x belongs to b. So, and then I can just rewrite yj again to xj, that is just a notation thing. And what I get is lambda expectation 0 summation over, and this indicator would just mean that xj belongs to b minus x. So this will be xj belongs to 5 intersection b minus x, and then you have to exclude point at origin f xj1 plus x. Okay, and if the point is ppp, point process ppp, then I can apply Slimnak theorem to equivalently remove this conditioning on 0 and this point 0 to get lambda expectation over summation of xj belongs to phi intersection b minus x fx comma xj plus x. Okay, now if you look at this, this is a stationary point process. So if I shift phi to x, that is not going to change the distribution. Okay, so I can equivalently again write it in terms of expectation of xj belongs to phi intersection b x comma xj. Okay, now if you look at this is just a summation over functions. Okay, some function x is a deterministic variable, so this is just a function of xj, and we are summing over it. So you can apply Campbell theorem here, and this will be equal to lambda integration fx comma y dy. Okay, and if you put it back, you will get lambda square fxy dy dx, and the outside integration with respect to a and inside integration with respect to b. Okay, so just a application of the previous example. Suppose I want to compute number of links. So in that case, I can just take function xi comma xj equal to 1, right? And so if I compute this, I'll get 1 for each link. So I'll get total number of links there. Okay, so if I right, so so this is expectation of number of links such that xi is in A and xj is in B, which we want to compute, right? And so first take the PPP case. PPP case we showed that is equal to lambda square integration of fxy dy dx. If I put 1 here, I get integration of dy dx, which is area of B into area of A. Total number of links would be lambda square A into B. Okay, for a general case, this is what we had, and you just put 1 here, right? So this summation over that is expectation, Palm expectation of total number of point in this set. Right? So if you look carefully, I'm going to each point in this set, adding 1. So there's nothing but a total number of points in this set. Right? So this is what it is here. Similarly, you can extend this to more pairs. So if you have a 3 tuples, you can apply Campbell-Mecke theorem, then for PPP case, then Slimnak theorem, then again Campbell-Mecke theorem, and then Slimnak again, and then again you have Campbell-Mecke theorem, you get the result, right? So for you can show that for n tuples in PPP, if you do it recursively, you can say that the summation of a function of n tuples, the expected value of that is given by lambda n into an n-dimensional integration of fx1 comma x2 comma xn dx1 dx2 dx. This is just a general result of what we saw in the pair case.